Unit 9, Day 2 Power Series. I was just actually going to finish up. We were about to do an example here with a Maclaurin power series. You have sine x squared, give the first four non-zero terms and the general term. So what's nice is if you take those terms that we kind of memorized, again, you could generate this sine of x term, but I would suggest that you kind of memorize the sine, cosine, and e to the x one. Those are the ones that kind of show up the most often. But if you needed to actually generate this, you could by using the technique I used for the day 1 video. But if you already know that this is sine x, then if you want to figure out a Taylor polynomial that models sine of x squared, then literally what you're doing is, because you're allowed to multiply them, you're just replacing all the x's with an x squared. So this is an x, you're replacing it with an x squared. This is an x, you replace it with an x squared. This is an x, you replace it with an x squared, okay? And then you're just going to apply those exponent rules. So inside, outside, multiply, so the exponent now is a 10, and so on and so forth. You're still going to have to apply that to the general term as well. So it said give the first four non-zero terms. So 1, 2, 3, 4. Those are the first four non-zero terms. And then you've got your general term. So if I replace this x with an x squared, remember now you're in the situation where you have to multiply this 2 by this entire binomial. So it's really like 2 times 2n plus 1. So if you distribute the 2 across, you end up with 4n plus 2. Okay, so that's how you do that on the general term. Now for part B, it says use your answer and now take the derivative. So this is kind of the crux of it, because it is easier to take derivatives of just a polynomial than it would be of some, transcendental function or something that's more complicated. So now we're using our answer up here, and now we're just going to take the derivative of that. The advantage of taking a derivative of a polynomial is you just take the derivative term by term. So 6 becomes the coefficient. It's still divided by that 3 factorial, decrease the exponent by 1, and so on and so forth. Now, keep in mind here, if you multiply this times that, right, this is still going to be some value of n, whether it's even or odd. So that's still going to say, but now it's going to have a coefficient of this exponent here. And then remember, you copy the variable, decrease the exponent by 1. So this exponent minus 1 gives you this 4n plus 1 divided by that. Okay, so that's still going to be there. So that's how you do something there. Very similarly, because one of the rules is that you can multiply, this time we're going to take a known Maclaurin of cosine of x, so this is like the known one, and then here we're multiplying each term by x. So it's a little different. Here we are actually replacing x with an x squared. Here we're just going to take this and multiply each term by x, because that's the operation there. So 1 times x is x squared over 2 factorial times x is x cubed over 2 factorial, right? Oh, there's a negative. And very similarly, when you're doing that with the general term, right, if you multiply this by x, remember the same base, you add the exponents. So if you have this to the 2n, and then we're like adding 1 to that, it just becomes 2n plus 1. So that's how you do something like that. All right, and moving right along. So now, up here we took the derivative. Now we're going to do them where it's asking us to use our answer from here and integrate it. So there is going to be kind of this switch of variables. Notice how now they're using the t's, but when we go to apply our fundamental theorem of calculus anyways, we'll be replacing those t's with x's anyways. So it's just kind of to show the change in variable there. So we're going to integrate this. Well, that means I'm trying to integrate this. Well, I'm going to use my polynomial that I use, so I'm literally just changing my x's to t's, right? And then when we integrate, we add 1 to the exponent, divide by that number. Add 1 to the exponent, divide by that number. Okay? And we're going to do that, and I can apply my fundamental theorem of calculus then. So I plug in x, so that essentially undoes that, when we replace the x's with t, that's going to undo it. Okay? And you can do that to the general term as well. Okay? Perfect.